linear algebra and calculus of how do Feynman diagrams appear. So I already started last time from the finite dimensional case, and then if you just consider the integral of the exponent where you have some quadratic part and then a linear part, then it's easy to compute. And then you just notice that if you just suppress this linear part here, but instead plug in a product of several coordinate functions, then such an integral can be easily computed using this one. Namely, just notice that if I would take the derivative of this exponent by bi and evaluate it at b equal to 0, that would give me just vi downstairs under the integrand. So if so, then I can, so this here is the definition. So this m-point function, or correlator of m coordinate functions, is just obtained by plugging them all here in the integrand. And then you notice immediately that you can rewrite it in terms of the derivatives of this integral here. So, and then finally, that's the place where the Feynman diagrams appear for the first time. Wick's theorem tells you that these derivatives of the exponent you can compute by summing over all pairings of these indices products of the elements of the inverse metric. It's here, A inverse. So then you can generalize your setup and consider already the function where I plug in some more general potential, your V, here in your action. So then, if so, then this U of V you can just separate into, take the exponent of U of V and take it power series expansion. And then you will always have integrals of this sort, which we already know how to compute. And then you combine them back into one function, into the exponent. And you notice that this is the exponent of u and of this differential operator, of u of ddv, applied again to the same function. Okay. And then I gave an example of kind of a cubic potential, u of v is equal to u I j k v I v j k. And we've seen then that to compute ZU, you should use graphs of the following sort. So they're all trivalent graphs, which looks as follows. Oh, maybe I should put here, sorry, H. Squeezing stage 1. So the graphs which appear in the expansion look like that. They are trivalent, all these trivalent graphs. Then whenever you're given a trivalent graph, you do the following. You put on each end of each edge, you put some index. Say I1, I2, I3, I4, I5, I6. Then on each edge of your graph, marked with I and J, on the end, you put the weight of A inverse Ij, and to each trivalent vertex of these labels I, J, K near it, that corresponds this ZU, you write, right here as a sum of the graphs, it's trivalent label graphs, and as h in the power the number of vertices of your graph, and then product of terms, product of all vertices, product of all ages first. Of these factors, A inverse of the age, where by A inverse of the age I mean this factor when the age is labeled by I and J, and then you have the product over all vertices of this U, I, J, K's, sorry, of the vertex, right? Which is a factor of this sort. And you should also normalize it by the number of the automorphism of your graph.
Which is normalized to the graph.
So yes, so let's see. So the graph of that sort would be, first I can rotate this. I can rotate this. Then I can rotate the whole picture. We have 3 possible automorphisms of order 2. So totally, so here the whole symmetry will be the number of automorphisms. Because I can also combine them. It's in 2 in power 3.
Also, in the product above, the vertices match that range.
You take the product of all vertices.
So the 2 products I see are completely independent.
Yes. Okay. Product, one product times each age gives you such a factor, and each trivalent vertex gives you it. You take them all over of the whole graph, and then you sum over all labelings also. So, so that was all last time. So, in particular, we've seen that this particular example of this cubic potential, the terms of degree h square correspond to just 2 graphs, one like this and another like that, which means that I have product of 2 u's, here and here, and then of product of 3 A inverses, okay, sitting on the edges. So for each of these graphs, just a second. So for each of these graphs, the term corresponding to it will be something like A inverse, A inverse, U, U, of this sort. And then these indices you put, as I explained last time. This is these are power series in H. Yes. Yes, it happens because here I should have the exponent of the series. So these are power series expansions. The number of vertices is the same here. Just know that it's the same as the number of independent loops in your graph, in the first homology of the graph. And that's called an n-loop term. The coefficient of h in power n would be called the n-loop term. It never converges. Just forget about all these things. We are going more and more physical. We just don't care about this stupidity. It's a form of power. Just never ask me again during my talk whether something converts. Never convert. Yeah. So, okay, so some physical jargon which people use usually talking about it. So I already told that this is called the endpoint function.
What if it's nice when you say that I to be divided v of I? Like function, v is a function
Of I, yes. That's what I'll do afterwards. I will now pass immediately to the infinite dimension. Okay, so that's what I'll do. Oh, no, it's called the correlation functions of these coordinate functions. Okay, now, these edges of our graphs are usually called propagators. So all these edges here are called propagators. Just because you think that you have some particles which, I don't know, here, well, two particles, well, or rather, something like, you think about these things as if you have two particles, say they collided, and then suddenly they probe again into two other particles, and about this process you want to think as about the propagation in space. Yeah, you know,
Are you going to tell us why?
why are they called propagators?
I mean, why you can interpret this is like everything.
Oh, no, You know, in general, what we are trying to do here is the following. So it's subdivided into physics and math. And here there will be time variable t in my space, and this will be before 90 approximately. Mathematicians would think about these objects, while physicists would always use these. And now after the 90s, we are in this new reality. And physicists think about strings and d-branes and whatever not, and we are down to this. Okay, so now, so let me just carry on with this example. The same example as I was doing here before. So same example. But now I would like to compute not just the partition function, but the correlator of, say, of two coordinate functions, v1 and v2. What will it be in this model? Well, what will change? Let's see what happens. How do these computations change, which we did for the ZU last time? The only difference, basically, is that between the partition function here and this correlation function is that I should take some number of derivatives of this guy. Now, the derivatives correspond precisely to these functions, right, to these coordinates. Which means that here I should take now two derivatives. So I would like now to compute 1 over z0 integral dv of the exponent of minus half dt v plus this cubic term there, ui jk vi vj k. But now, in addition to this exponent in the integrand, I have also product of V1 and V2. Which leads me now to two additional derivatives. I should take the derivative by V1, V2, and then whatever I had before, which means, so I still have this Z0 will disappear because I subdivided, but I'm left with the previous expression, which was here. So it's the exponent.
So you added the cubic term.
Yes, it's the exponent of ui j k d dbi d db j db k h bar. Thank you. R, it equals to 1, right? So NB equal to 0.
Some people actually take derivatives from what?
Right,
Oh, man, you.
the other way is that we want to not be
What do you want here? Or you want me? Hmm? Here. Oh. 3. Yeah.
Am I wrong to be worried about the fact that this interval doesn't converge?
Hmm? Huh?
No, but it does. Right, it doesn't converge. It's a formal power series. Well,
This will be.
the interval therefore actually is
No, John, the definition is inside of the formal power series, integrate term by term. That's the definition of what it's talking about. Each of those coefficients are going to converge.
Isn't there an exponential of how these two angles is?
Yes, indeed. Did I lose anywhere half again?
You didn't write what you estimate.
Ah, yes, I never. Oh. That's even too physical, yes. So X of half B and inverse B. So this operator is applied to this exponent and then we evaluate it at B. So the only news are these two derivatives. Now, how do we see them if we try to write everything using this Week's theorem in terms of graphs? So if I would write here, again, by Week's theorem, sum over graphs, now what kind of graphs which, well, these, see now, so in my graph, if you remember, the end of each edge was labeled by some coordinate. So this time I have two new derivatives which lead to two new kind of ends of two edges. So one is labeled by V1, another labeled by V2. These are two ends, and then I have some other trivalent graphs. Okay, some kind of trivalent graphs here. So the only new thing here is that when I talk here about graphs, so then these graphs will be the following. So I have graphs with two univalent vertices. Which are labeled by V1 and V2, or rather by 1 and 2 if you like. Sorry, maybe better to say just by 1 and these univalent vertices come from these two derivatives. And apart from these two derivations, everything will remain the same as before. And say n trivalent vertices and whatever number and the rest and all other vertices trivalent. And then you do the same as before. So you write here h in power n, where n may be among all other n vertices are trivalent. So h in power n over the automorphism of this graph times the product over all h's of this A inverse of the h, and then product over all vertices of this u I j k u of the vertex. But these I understand only as trivalent vertices. So here they're only trivalent vertices, where I should take these factors on here. So the graphs look very similar, but now I actually lied to you in some place. So let's see where. So let's just see what will happen again. Two-loop contribution. So I'm looking in the terms with n equal to 2, the coefficients of h squared. Which graphs will I have then? Well, my graphs are always have these two univalent vertices, and they should, in addition to that, have two trivalent vertices. In particular, I have this graph, I have, say, this graph. These vertices are labeled by 1 and 2. The rest is labeled somehow, and I sum over all labelings. But there's now, let's see whether the following diagram will also appear. What about this one? So here, this is a graph which consists of two connected components here. One is just a straight line connecting 1 and 2. There are no trivalent vertices there. And then there's another separate component with two vertices. So this type of things we call vacuum diagrams. Vacuum diagrams. And this will stand for any diagram where there is some connected component which has only trivalent vertices. So it's not connected, neither to 1, neither to 2. Something of that sort. Now, whether these terms will appear or not. So I say now that no, they will not appear. Now, just the question is only why. And the answer is because I normalize it here by 1 over z naught. Now, what was this normalization by a 1 over... oh, sorry, this is not z naught. Oh, this is stupid. It's zu that I should normalize. I'm extremely sorry. So, I'm very sorry. Zu is the same thing. Yes, zu, which was there, it's the same thing precisely, but without v1 and v2. Okay. Without these two univalent vertices. And then in zu, as we discussed before, we see graphs of that type, right? So, because we normalize by 1 over CU. And in the CU gave us the graphs, which in particular looked like that, right? It was 1 plus this graph plus graphs with more vertices. But this graph already entered in the expansion of CU. So when I normalize here, such terms will just disappear. I will divide by these quantities. So I will be left only with graphs where each vertex is path connected to the univalent vertex, to at least one univalent.
So, but you should also do this last thing.
What's the second? This?
Back. So how is it?
Yeah, but I should write it here. Here by, well, it would be Z naught over ZU. Sorry, I forgot this ZUF. That's about Z naught over Z. Just forgot to normalize by the ZUF. So the lesson which we are supposed to learn from this is the following, that in general the Feynman rules in this example should look like that. Feynman rules for this example for U.
They are the description of the graphical algorithm computing the
The Feynman rules are just this description of the graphs which appear in your expansion and of the weights which you put on the edges and vertices of the graph. So these are,
What order do you take this in if you want to go out
depends on your age. I mean, these are power series in age, so when you just want to take, linear, say, term, then 2-loop term, 3-loop, so you just go up to certain power of age. So general Feynman rules here would be the following, that if I want to compute VI1, etc., VIM, I should do it by counting unitrivalent graphs with univalent vertices, with M univalent vertices labeled by I1, etc., IM. And all the others, all other vertices trivalent. And then again for each edge of your diagram. Yes, so as I said, no vacuum diagrams, which means that each trivalent vertex can be path connected to a univalent vertex. So diagrams of this sort do not appear. And as I said before, for each age labeled by ij, you write the term of A inverse ij, and to each trivalent vertex labeled by ijk, you write a factor of uij. So these are the Feynman rules in this example. they tell you how to compute m point function. So with the univalent vertices, they're just there, right? And they're labeled by these ui, etc., um. So where do they contribute? Well, they are univalent, so they don't contribute any factor of that sort. But these are endpoints of some of m ages. So they just contribute factors of this sort. So there will be m additional factors of this sort coming from the ages. So your diagrams look like that. I1, m, and these m ages just give you additional m factors of a. These are the labels. Okay, so let me already move to infinite dimensional spaces. Okay, so the case of infinite dimension. So I would like just to give some small dictionary. And since in infinite dimensional cases, these things, you just work with some path integrals, which are not well defined mathematically, just don't ask me anymore about any convergence. Everything will be an even more formal power series than before. So, okay, so what about the infinite dimensional case? Well, just a little dictionary for translating everything is as follows. So, suppose I have the finite dimensional case, I have the infinite dimensional case, and I would like to translate several things from here to there. So, finite dimensional case, we had all these indices, finite indices I, which ran from 1 to the dimension of our space, these. Yes. Now in this infinite dimension, instead of this discrete index I will have a continuous index x. This will be x, and x will live in some manifold of dimension d, or we want to say Rd. I don't even care, it may be not open.
That's like RD minus 1 plus R, space time.
Yes. So this is analog process.
Now on space time.
This manifold is the space-time union. So just the general idea is that instead of these discrete indices, you now plug in everywhere these indices. So if so, then whenever you had the summation over these i's, now it will be integration over dx. Now, if you had v, now you will have, so v was a vector, right? So you can think about it as this v as a function of this I, right? Because it was a vector with all these coordinates. So I would like it to write v of I. So here it will be, instead of I'll write it, call it phi, and it will be phi of x. Okay. What else? If I had, say, A depended on two indices of I and j. So A I can write as A of I and j. That was my quadratic form, the bilinear form. So then here I will call it instead K. This should be the kernel, which depends on two variables, facts and y. Similar way, B, which was a vector, so it again depended only on one coordinate, will now be some function which I'll call j of m, just of one variable. Good. Now, continue.
Does this use K or G?
I don't know. You want G?
No, it's just
Go on.
Green's function. I would say Green's function.
Okay. Well, I would like to keep it for inverse, for the inverse.
Yeah, G is Green's function.
Of the inverse. So I would prefer it to keep it for the inverse. So let me go on with this dictionary. So far, I just exchanged all the discrete indices. So now, what will happen? What is my, say, the analog of my linear form of this VTAV? How should I understand it? Well, it's the summation over i's and j's of v I, a, I, j, v, j. Right? So I will just write it as v of I, a of I, j, v, j. So now, what will be its analog? Why wouldn't you tell me? What's its infinite dimensional analog? D of x, d of y, phi x, k of x, y, phi of y. It's just straightforward translation using this dictionary. Summation is everywhere exchanged for the integration. And I just, instead of these guys, B never appeared. Okay, now BT V is in fact the summation over I of B, say I, V, I. So here its analog will be the integral of dx, j of x, phi of x. Okay, now so what will be the analog of our ZB, which was the integral dv the exponent of minus half VTA V plus VTV will now be Z. What will be the subindex? J. Yes. And then that will be the integral over Now, this is a tricky thing. This means that this is the path integral. I integrate over some spaces of functions. This is really bad thing. So, well, yes. So now there's the x. And here there will be the action, so it will be minus half. And I will just write this, all this integral, as phi k phi, where I am this integral. So I will call it phi k phi. So this is double integral. And then plus the term which should be instead of bv, and we've seen what this is. I'll just call it k phi. Okay. So far so good. Now we knew how to compute it. Right? We have some formulas for that. So, would I write? I like to do it. Oh. Okay, now, you see, maybe I will just immediately pass to the correlation function. Huh? Yeah, I can plug it in here, H. Yeah, so I already think that my potential there will be in powers of H. The potential will be more general, right? It will be instead of this B. So the correlation function of, the slightly more general case, it was this ZU, and it was almost the same, only here I had some potential U of V. That's some general potential. Then it's the same, only here I should call it something. I'll again call it ZU. Here the potential will depend on phi. Some function. Say phi q. So for this thing and for the correlation functions, we have seen then how to write the Feynman rules. And then we use the Week's theorem. And the Week's theorem, remember that I have to use always A inverse. Now, what is the analog of A inverse? So I will call it G, K inverse in a sense. In which sense? So it's the inverse operator. So here, what was the property of A inverse? It meant that A inverse times A is what? If I put here ij, maybe ik, kj, and I sum over all k's, I should get delta ij. So here it means that the integral over dz of g x z times k of z y equals to the delta function of x minus 1. X comma. Yeah. So this will be the object which will appear on each edge of my Feynman diagram. This will be the inverse, the green function of the inverse of this K. So, and another thing which maybe I would like to mention, that before this A inverse, I could compute very easily like that. I could take A inverse ij and say that it was the second derivative dd bi dj of z b and b equals to 0. So here I will have the same. So it will be, j, g, now you'll see something new again. So x, y means the derivative dj x dj y of z b and b equal to 0. That's it. And j. Now, so there's something new again here, right? These derivatives. So these are just functional derivatives. I will not say much about them since it's kind of supposed to be polynomial. So let me just define them. So what are the properties of these functional derivatives? So they're defined like that. So I will just define it by its property. Okay, so djx is linear, which means that if I apply to a sum of two functions, say of x of some f of j of x, whatever, plus x will be
G is best because G is green function.
so it's linear and the usual sum. Then it is a derivation. So it satisfies the Leibniz rule. And then I should also say that djx of j of y equals delta x y. But it's just the analog of it's ddxi of xj. So so these properties do define it uniquely. So, and maybe I'll give here an exercise. So, exercise. It's a nice homework to compute dj of y of the exponent of integral dx j of x phi.
Z sub j actually does make sense. Z sub j is actually that's naturally pretty well defined. No, it doesn't make that. Does this partial derivative actually make sense?
These functional derivative? Yes, of course. Sure. Yes, it's calculus of variations. It's just variational calculus. You know, you just write. It just means the calculus of variations. So you can just say that you take so d of dj, say of x of some whatever function of f.
And what works is that I have trouble imagining varying j just in a single point. See how it's appearing under
No, but you do it everywhere. So you just define it similar to the usual derivative. Only then under f you define it to whatever it was plus epsilon j of x minus without minus f of whatever it was over epsilon.
So there's the x. What happened to the x?
That's actually wrong, because the second thing, when you take the limit, you should get the integral of that over x. That's the integral kernel of the differential.
Whoever did variations, of some functionals, just think that it's that I just take delta of f of phi.
Yes. So
And then the linear term, so it will be proportional, there will be term proportional to delta of j of x and something else.
Yeah, so it's a real escape.
Yeah.
Yeah.
The limit.
Where is the x in that?
Just think about the usual derivative, the usual coordinates. And then you take the infinite dimensional analog and just think how can you define this analog. By which properties, whether it will be well defined, how to define.
Are we to take that
It's some
X series?
standard thing in functional derivatives. I just cannot
We're
really.
not to take that X series, right? In that formula, there's an X in the top and none in the bottom. So that X is kind of formal. Whereas in some of these things, it seems not to be.
I think the easiest thing is to think about it as that. Think about it as it's a distribution. The result is a distribution. Think of the whole thing as the integral of dx times the test function dx times delta bar delta x, delta bar delta gx. That operator operates on f of phi. If you do something, and that something is just f of phi plus exponent times the test p of x minus f of phi upon epsilon. So that's the unit distribution, which you call delta bar delta jx.
Right. So that's sort of the formal integral kernel of the differential.
Yes.
in the-
Yes,
in the ordinary
yes.
sense. So in some sense, there's an integral over x with the j in there dx. So it's just like it's the gradient of the direction.
Well, just a minute. This is not what we should be learning from.
Yes, I'm sorry.
There's a pattern here which, if you go in, these
I
these
hope
expressions,
that-
you come out with the answer, we have to think about the whole pattern and go back and make
And-
what then you want.
I'm trying just to get to, say, to the final rules. So this is some. I really don't want to enter too much in these definitions, rigorous definitions, but this you can find in any course operational calculus. So now we can again use this Wick's theorem, etc. So now what will happen? So what will be the analog of our old?
That would become the theorem of the definition.
In a sense, yes. So since the original object was very badly defined, we see here some path integral.
But that is well defined. At
This.
least when you see is small.
Oh.
That measure really exists.
Oh, okay. All right. It very rarely is well defined.
Because of the U, it doesn't exist.
Yeah, well, as long as it was just linear, which is his
No,
situation.
no, but the point is it doesn't exist in the case of Quant, so we're going to interpret it these small.
And D5 is not existent.
So
And when you go to a bowl of fruit, pick out the fruit needs it. Do that.
So now, let's see. So, what will be the analogs, by the way, of the endpoint functions? And what will be the Feynman rules? So, first of all, the endpoint functions, there will be now functions of the coordinates again. So before, these were coordinates vi1, vi2, etc. So now these are just phi's in different points. So before it was, so I just recall that before it was, maybe I should write it here. So before I had vi1, so which I will write now like that, etc. vim equals to something. Now, these v's are now called phi's, and these discrete indices move to x's. So this will be x1, xm. And this will again mean just plugging in the product of these functions under the integral here. And this exponent, in addition to the exponent, I will just plug in the end, the product of these functions. So it will be 1 over z of u of the integral d phi of the exponent. These x, y's, and z's, etc. Yeah. X. Not enough. Yeah, well, these are pass all possible m letters. So here that was the exponent, the same exponent as I had before that, right? This, just this thing here. D phi exponent of minus half phi k phi, which I already should understand that there is a double integration there, right? As explained before, plus u of phi. And now in addition to that, I take the product with phi x, etc., phi z. Yeah. So these are the correlation functions. Now, how to compute them by Week's theorem? Well, so I will already read just the Feynman rules, so I'm running out of time. Hmm? Here, yes, these are fixed. Those are fixed points. Okay. Yes, yes, these are fixed. It's just precisely as I fixed these. Okay? But over the rest, I will integrate. So what will be the Feynman rules? So let me again take some example. So the example, which will be phi cubed. So it's this cubic potential. So let me take it just the simplest possible. It will be u of phi is just phi cubed. Huh? The integral. Yeah. Just, yes. Let me go. Let's take that. That's just the infinite dimensional analog of this cubic potential which I explained before. Right? So let's just see how to change our Feynman rules. Now, before, which kind of graphs did we have? We had m univalent vertices. Okay, so now again I will have m univalent vertices, m univalent vertices in my graphs, and they were labeled then by these indices, I1, etc., up to IM. And I fixed these indices. There was no summation over them. So now these indices are x, etc., up to z. So these x up to z are some indices which stand on these univalent vertices, and these are fixed. There's no integration over them. But then I had also some graphs inside here, had some trivalent vertices here. And here on each trivalent vertex, I would put some indices, I, j, and k, and I would sum over them at the end, over all these labelings by indices. So now these edges, if you wish, they will be colored instead by the points of the space-time. So it will be something like P, R. So I just, and there will be again the rule precisely as it was before, that if I had the cubic potential, and here I have again say cubic potential, I should do it in say U, P, R, and J. And each edge would be colored by two indices, but again, instead of discrete indices I and J, these will be points on the space-time. So it will be some kind of P and Q, and to each edge that should correspond the factor. Before it was A inverse, so now it will be this green function, G of PQ. Maybe I should write.
You say what the UPQ are?
Well, it just depends. Here I took the... Let me take, so I, in fact, this little integral and whatever it is. So U of phi will be now, instead of the sum over ijk's, I will have integral over P, yes, Q and R, and here there will be U of P, Q, and R times phi of P, phi of Q, phi of R. So in general case, if I would like to write cubic potential, it should be cubic potential on three different points, and these should be the coefficients.
Where does this function little u come from?
It's given to you. When you, for instance, huh?
Because you wrote U, capital U of phi is very
It's phi cubed. So in this case, it will be very simple because then all these three should be the same, which will means that U of P, Q, and R vanishes whenever these indices are different. And it just equals to 1 when they all coincide. Okay, so this delta function, sorry, of the diagonal of 3 variables. So these will be the Feynman rules again. So note that before I had to sum over all the labelings which I had on the edges, right? For all except for markings of these vertices. So now what will happen? I will have integration instead of the summation, and these discrete indices ijk's which I had will be now the points in our manifold in the space-time. So there will be integration over the space-time over all the labels which I see here on the internal ends of all internal names. So that's basically the, if you wish, definition or a recipe of some perturbative series of some graph. And these are called